Hi, and welcome to the next lecture of the course, and we're going to continue our discussion of mutations occurring in N species environment. We'll just carry forward the framework that we had ended up on in our last lecture, and we had ended up, and I want to spend a little bit more time on the variable Qij that we had talked about. So we have a bunch of genotypes, genotype A, B, C, all the way going up to N, and when A replicates, it could either lead to a genotype A, or via mutation it could either lead to genotype B or C or I or N. So in this map we are interested in two distinct type of arrows that we have happening here. One is all the arrows which are leading out from a node, such as this. So remember, Qij was defined as the probability that genotype I on division gives me genotype J. So by that definition, this arrow represents the probability that when A divides, I get back genotype A. This arrow tells me that when A divides, I get genotype B. This represents that when A divides, I get genotype C, and so on and so forth, leading all the way up to QAN. That genotype A divides, and that gives me the resultant progeny is of genotype N via mutation. This arrow here represents the case that no mutation has happened during the replication event, and all these arrows here represent the fact that during the process of replication, error had happened and the progeny is carrying a genotype which is distinct from the genotype of the parent. One quantity that we should note here is QAA plus QAB plus QAC going all the way up to QAN. I would recommend that you pause the video for a few seconds, think about what this sum should be, and then restart the video. In the representation that we had talked about, this can be written as sigma. I varies from A to N QAI. And this quantity should be equal to 1. And that comes from the fact that every time replication of A happens, it has to commit to one of these N arrows. Replication of A would lead to a progeny being generated, and that progeny is going to belong to one of the N genotypes which are present in the environment. What is the chance that the progeny that has been produced belongs to genotype A is represented by this number. The chance that the progeny that has been produced belongs to genotype P is represented by this number, and the chance that the progeny is of genotype N is represented by this number. But the fact is that the progeny has to belong to one of the N genotypes which are present here, and hence sum of all the probabilities that the progeny belongs to one particular genotype has to be equal to 1. So sigma QAI, I varying from 1 to N, is equal to 1. And this is going to come in handy as we move forward with our analysis. So now when I'm looking at an individual genotype, let me just draw that very quickly. This just helps us keep in mind pictorially what's going on with the system that we are talking about. I'm drawing arrows leading out of only node A, but the same is going to be the case for every particular node, that when B divides, it could lead to progeny of type A or C or N or itself, and so on and so forth. Now these arrows that are there, I have quantities QAA, the probability that progeny is of type A when division has happened with the parent A, and QAB going all the way up to QAN. Again, I suggest that you pause the video for a few seconds and just try and think about the relative magnitude of these two quantities. Quantity 1 is the variable QAA, and quantity B, quantity 2, is the sum of QAB plus QAC going all the way up to QAN. Basically, this sum includes all the QA terms except for the QAA terms. So I suggest you pause the video for a few seconds and think about the relative magnitude of quantity 1 and 2 that should exist as you understand microbial physiology. If you've thought about this, what should become apparent to you that what we have talked about so far suggests that 1 is much bigger than 2. And that's because if you remember the E. coli mutation rate that we were talking about, which was 10 power minus 3 mutations per genome per generation. Which means if this was E. coli replicating and you had node A as your parent E. coli, if you had 1000 divisions, 1000 such replication events happening for division from node A, 999 out of them are going to be identical replicas of the parent genotype that was being copied, and only one of these 1000 replication events is going to be distributed to the remaining n-1 edges. Which one of those n-1 edges is something that we don't know because mutations happen randomly. It could be either one of the n-1 edges here, but the point is that these numbers are so skewed that quantity 1 is much bigger than quantity 2. That's something that's very important to realize. We should also realize that some quantities QAI may be equal to 0. This is possible because so far we are only talking of mutations occurring via point mutations, which are single nucleotide errors which DNA polymerase is making. If that's the case, then it's conceivable that genotype A gets mutated to genotype B. This happens via one point mutation. Let's imagine this is an nucleotide A changing to nucleotide T, but B then mutates to genotype C, and this change happens via a G changing to a C at another place on the chromosome. So these two mutations that we are talking about are happening at distinct locations on the chromosome. What that means is that when genotype A replicates, there is no way that it can lead to a progeny of genotype C, provided that the maximum number of point mutations that we are allowing per replication event is equal to 1. A cannot lead to C if only one nucleotide change is taking place in the progeny. To lead to C, A has to go via B. It has to first lead to change of an A to a T at one location, and then at another location on the chromosome, G has to change to C so that genotype C is produced. Hence, what that implies in this example is that QAC is equal to 0. And you might have several more quantities which are 0 depending on what are the precise mutations that link each of the n genotypes that we are discussing. So two important things come out of this discussion. That first, the QAA, the self-replication arrow, is the most likely arrow of division that's going to take place in the system that we are talking about. And some of the other arrows in this system, the way we have defined them, may turn out to be 0 if there is no way that genotype A upon replication, and we are only permitting one nucleotide change, maximum mutations to take place, can lead to C genotype in one go. So having understood these, let's try and formulate the dynamical equations associated with these n species. Let's start with dxa by dt. dxa by dt would be, imagine again, let's for the sake of clarity draw the picture once again. We have genotype A, B, C, N and I, and we have A leading to A leading to B, C, N and I. What influences the number of A's that are present in the population that we are talking about here? So to account for the number of A's in the population, we are going to be interested in all the arrows which are coming into node A. This is one arrow which is coming into node A, which is every time A replicates and it leads to a progeny of type A. What is this going to be equal to? This is going to be represented by x1 xa times QAA. It's important you realize this, that QAA is the probability that when A divides, the progeny is of genotype A, and XA is the fraction of individuals which belong to genotype A at that particular instant. So XAQAA represents how many progenies, what fraction of progenies that are being produced are incoming as defined by this particular node. Similarly, you are going to have division of progeny of genotype B, and that via mutation may sometimes lead to a progeny which belongs to genotype A, and that's going to be represented by XB, which is the fraction of population which is of genotype B, times QBA, which represents what is the chance that whenever bacterium of genotype B replicates, the progeny belongs to genotype A. And so on and so forth. We come to XI, which is the fraction of population which belongs to the ith genotype times XIA, representing the probability that when I replicates, the progeny belongs to genotype A, going all the way up to XNQNA. Make sure you spend a couple of minutes studying this equation and convincing yourself that this represents the change in the fraction of population which belongs to genotype A with time. Alright, so let's maybe try and write one more, which is dxb by dt. And now when we are talking of node B, what we are interested in is all the nodes, is capturing the dynamics of all the nodes which are incoming to B, where divisions are taking place of various genotypes in the environment, but the progeny being produced is of genotype B. These are all the arrows that we are interested in. So first off, we'll start with this arrow, that division of a parent of genotype A leading to a progeny of genotype B, and that's given by XA times QAB. frequency of genotype A times the probability that when A divides, the progeny belongs to genotype B, plus XB times QBB. This represents this arrow where B divides and the progeny also belongs to genotype B, and again going all the way up to XN times QNB. Again, I suggest that you take a couple of minutes and write an equivalent equation for dxi by dt. What that means is, now you are interested in all the nodes which are coming into any ith genotype and account for its rate of change of frequency with time. Once we have this, we will obviously have n distinct differential equations which capture the dynamics of these n coexisting species. So, and we can write them afresh, and I'll write 2, which is dxa by dt equals xa QAA plus XI QIA going all the way up to XN QNA, going all the way up to dxn by dt equals XA QAN plus XI QIN plus XN QNN. In all, these are n differential equations. And in order to arrive at the steady state associated with this dynamical system, these n differential equations have to be solved simultaneously. That's what we would do to arrive at the steady state of this system, and then we will have to analyze the stability of those steady states and decide what are the frequencies at which the system wants to stay at, which is not a trivial task. And what we are going to do now is take help of concepts from linear algebra to simplify this system further and see if we can get any insights from there. So, linear algebra, we are going to write this differential equation in the form of a matrix, and if you look at the left hand side of the equations that we have just derived, you will see that all we have on the left hand side are n particular derivatives for representing each one of the n species. So the left hand side are just n derivatives, and so the left hand side of our linear equation is going to be this n derivatives, dx1 xa by dt, dxb by dt, and so on and so forth, going all the way up to dxn by dt. That's my left hand side. What's on the right hand side? Let me take a look at my equation. I have a factor QAA multiplying with XA, but I also have a factor QAN multiplying with XA. That's the first entry for every equation. For the ith entry of every equation, I have a factor multiplying with XI, I have another factor multiplying with XI, and for the last entry for each equation, I have a factor multiplying with xn, and I have another factor which is multiplying with xn. This tells me that this system can be represented as the product of a matrix and a vector. And my job is to find that matrix and that vector which represents this particular dynamical system in a linear sense. When we do that, let me say this is the matrix that is still unknown, and this is the vector that I'm talking about here. and the vector can be sensed from the fact that the first term in each equation is multiplied with xa, the ith term in each equation is multiplied with xi, and the last term in each equation is multiplied with xn. That gives me a clue about what should be the nature of this vector, and that should be xa, xb, xi going all the way up to xn. That's the vector that I'm talking about. Now what I want to do is find the elements of this matrix. Let me look at my first equation. My first equation is dxa by dt, which is this entry, and the first term is that xa gets multiplied with qaa. Remember that when a matrix is multiplied with a vector, the first row multiplies with the column vector, and that gives me the first entry here. And in that first entry, xa is multiplied with qaa, which should be the first term of the matrix, which is qaa. This is followed by the second term, which will be xb into qab. I have xb here. That means the second entry here should be qab. Going all the way, xi should get multiplied with qia. I'm sorry, this should be qba, because we're interested in whenever replication of B happens and the progeny belongs to genotype A. So this entry here should be QBA, IA, and the last one here should be QNA, which is division of genotype N happening and leading to a progeny of genotype A. That's the first row. Similarly, we can go on and we get the last row as QAN, QBN, QIN, QNN, which represents that whenever genotype I divides and leads to a progeny of genotype N, that's represented by the probability QIN. So that gives me my matrix structure, and this matrix is called the mutation matrix Q. Okay, so this is my mutation matrix. What am I missing so far? You should ask this question at this point and realize that something that we've been talking about throughout is not been incorporated in this equation, which is what is in every time we have talked about growth equation, we have incorporated the variable phi. We haven't done it at this point, and we need to take into account phi. And remember, the growth of each equation is growth of every particular genotype is represented by what is being added minus phi times the frequency of that particular genotype, which is phi times xa. The equation here will be phi times xn, and so on and so forth. Right? So the complete equation, which takes into account and which enforces that the total number of individuals gets constrained to k, total number of individuals belonging to each genotype when added together does not exceed k, has to be taken into account, and that leads me to my final equation, that dxa by dt, dxb by dt dxn by dt is my left hand side, which represents the rate of change of frequencies of all n genotypes associated with the environment. This is equal to q times q, which is my mutation matrix, times the vector XA, XB, going all the way up to XN, minus phi times XA, phi times XB, and so on and so forth, going all the way up to phi times Xn. And phi, in all our discussions, we have always found that to be equal to the mean growth rate of the individuals in the environment. At a particular time. That's what we've realized the significance of phi to be, that it represents the mean growth rate associated with the environment at any particular time t, depending on the frequencies associated with each genotype. And because similar to the two species mutation that we were talking about, here also every single genotype is growing with a growth rate A. So since growth rate of every genotype is equal to 1, that means mean growth rate is also equal to 1. And this mean growth rate equal to 1 is independent of what is the composition in terms of the vector x at any particular time t, because no matter what is the composition of the population at any time t, every single genotype is growing at a growth rate 1, and hence the mean is always going to be equal to 1. So phi for our case is equal to 1. What this means our system reduces to is the following equation: dxa by dt, dxb by dt, going all the way up to dxn by dt, equals q, which is the mutation matrix, times vector x minus phi, which is just 1, times vector x. Vector x here represents xa, xb, going all the way up to xn, and mutation matrix is as we have defined in the previous slides. And to arrive at the solution of this equation, we have to first look at the steady state, which would imply that all derivatives defined to the left hand side are equal to 0. That means to solve this system, we have to solve the following equation: 0 equals mutation matrix q times vector x minus x. This is the equation that we need and solve to solve the mutation between n distinct genotypes at any given point in time. And that's not a trivial task, and we're going to borrow help from concepts from linear algebra to be able to arrive at this solution. And that's something that we're going to pick up in our next lecture onwards. We'll stop here for this one. Thank you.